So the next topic is network covalent atomic solids, or just network covalent solids. And we're going to be looking at carbon, and carbon actually makes, in nature, a number of different forms, and these are known as allotropes of carbon. So different crystalline forms, or different elemental forms of carbon that exist are all known as allotropes. And one of those is graphite. We talked a little bit about highly ordered pyrolytic graphite before, and its role in producing graphene. And so graphite, when you look top down on it, that is, you're just looking at the structure from the top, what you see is a set of hexagonal rings that look something like chicken wire, actually. And every single atom in graphite is sp2 hybridized. So in every single one of these carbons, which is what we're seeing here, there's a p orbital that's unhybridized. And it's part of the pi bond system, is what we call it, for graphite. And every single carbon in this structure is connected to each other through a large pi bond, or pi bonding molecular orbital. What that means is graphite can actually conduct electricity through these open p orbitals because they're all overlapping with each other on the entire structure. Now, if you look at graphite in 3 dimensions, that is, you lay it out like this. Well, this is a chunk of graphite, like a piece of charcoal almost. Not barbecue charcoal, but like a piece of coal, right? It is composed of layers of graphite. Like, these are graphene sheets. So graphite is made up of layers of graphene sheets, which give it a lot of strength. Let's say trying to pull on end to end, but it also makes it really slippery material because these interactions between the graphene sheets are just weak intermolecular forces, so they actually can be slid past each other. That was, in fact, the secret to being able to get graphene out of pyrolytic graphite, is that you can just take a piece of Scotch tape and touch it to one end and lift it, and you get these super thin sheets of carbon coming out, and occasionally you're able to get one that's just one atom thick, and that's what they were studying when they were doing their work on graphene. Now, diamond is a little bit harder to understand. Pictures don't really work well, so I pulled up this movie, and I'm not really even happy with this, but this gives us an idea of the structure of diamond. We'll talk about diamond's crystal lattice in a second, but diamond is actually a lot more dense than graphite, and you can form diamonds from high pressure and high temperature. And what you can do is basically force the rearrangement of graphite's bonds to form diamonds. So you now, instead of having layers that are separated from each other, all the layers are interconnected with each other. We find diamonds deep underground, but that's over long periods of time. But if you want to speed up the reaction, you just use high pressure, 50,000 atmospheres, which is quite a bit, and around 1600 degrees Celsius, and that'll form the graphite, or convert the graphite into diamond. Now, the diamond unit cell, this is actually a thing, so we're not just sort of generically referring to it. This is the name of this unit cell, and there are many compounds that have the diamond unit cell. Looks a lot like zinc blende. If you remember zinc blende, what we just looked at before, there's 4 atoms on the inside. Well, in diamond, there's 1, 2, let's see if I can count them out right. Actually, these ones, 1, 2, 3, 4 in the unit cell. But then you have a whole bunch. These ones that are shown here, these are all in the faces. And then you have the ones at the corner. Unlike zinc blende, though, these are all carbon atoms. And they're all covalently bonded to each other, is what allows them to be really strong. I'm going to show you something here really quick. This is a molecular simulation of graphite. Or of diamond, I'm sorry. So you can see, actually, if you look at diamond at the right way, it kind of looks like it's hexagonal. I'm going to zoom in a little bit, and each one of these carbons, I don't know if you can see, there are layers of carbons here, is tetrahedrally shaped and bonded to 4 other carbons. And I'm going to try to turn this so you can see that. Okay. And so I'm going to turn it. And we're going to focus on this guy right here. He is connected to the layer at the top, and he's connected to atoms in the same layer. And then each one of those is connected to atoms in the lower layer. All right, so you can see that interconnection when you go like this. It helps to be able to go backwards and forwards a little bit, so you can sort of pick on one and sort of look at it and see how they're all interconnected. So it's this structure that makes diamond super hard, very rigid, gives it a really high melting point, and those properties give it a lot of different uses. Sorry, I just sort of lost my words there. I should also point out the interconnectivity of the layers also gives it really nice thermal transfer properties, so good conductor of heat as well. So another allotrope of carbon is one that you're probably familiar with, this picture here. It's the buckyball, or the Buckminster fullerene. And it's a soccer ball shaped cluster of 60 carbon atoms. It's also known as, you'll see this built in building structures called geodesic domes. And so it was actually sort of discovered by accident. They were doing spectroscopy on a carbon source, and they noticed that they had these weird, very large, right, pure carbon signals in a mass spectrometer. And it turns out the only reason that hadn't been discovered sooner is nobody knew that it existed. It had been around for years and years and years. In fact, when you look in soot, like from a fireplace, you'll find some of this kind of stuff in the soot in a fireplace. So fullerenes, right, contain clusters of 36 or more than 100 carbon atoms in some sort of spherical type relationship. The generic name for them is buckyballs, which seems to have caught on pretty well. And then this is graphene down here, right? It's a layer of graphite. And what scientists have figured out how to do is actually produce what are called nanotubes. And basically it's graphene rolled up into a tube shape. And the way they form this is they actually take a solid surface. Usually it's the ones that I'm familiar with are like silicon wafers that are doped with a metal ion. So doping just means you put a small amount of metal ion on it. And the one that I've seen is nickel. And what happens is nickel acts as a catalyst for a particular reaction, forming carbon-carbon bonds. So they have this nickel catalyst, and it catalyzes the formation of carbon-carbon bonds. And what you see happening over time is that structure forms and the catalyst sits at the top. And the way they do this is they do what's called vapor deposition of carbon. So they create a plasma of carbon over this surface with the catalyst on it. And over time, what those catalysts will do is they'll insert more carbon-carbon bonds underneath themselves. And these things grow up like hair on a surface. Dimensionally, they're very thin, but they have extremely high tensile strength. They're much stronger than steel, with a much lower density because it's made out of carbon atoms and not iron and nickel and chromium, things like that. Speculation is, you could. This came out about, 10, 15 years ago. People were talking about building an elevator to space, and what they were going to use for the cables were these called single-walled nanotubes, carbon fiber nanotubes is what they called them, single-walled carbon fiber nanotubes, yeah. And they were going to make these, if they could make these long enough, they could make cables out of them. They're extremely thin, very difficult to work with, and actually they pose something of a breathing hazard when you work with them. What they typically get instead of this, though, what the more common thing to get is something that looks like this, and this is known as a multi-walled carbon fiber or carbon nanotube. Yeah, multi-walled carbon nanotube. And this is multi-walled because it's this structure, the single-walled nanotube, but it's just repeated out in layers around the initial tube. So you just get a whole bunch of these tubes built up around each other. Again, they have the same properties of as graphene or graphite. They're electrically conductive, so people have used them, for example, as small wires to connect to enzymes and other kinds of interesting substrates. Anyways, these are, again, different allotropes, different forms of carbon that can be created in the laboratory but naturally exist as well. So the next group of network covalent solids that we'll talk about are silicates. And silicates are basically sand. You take sand and you heat it up, and it forms a molten blob. That molten blob is what we turn into glass. And so silicates are very common. 90% of the Earth's crust is made out of silicates, implying their great stability, right? They're very stable. Generally, the silica, which makes up the silicates, has a formula of SiO2. And you'll notice that this is one unit of a silicate, and they have a silicon in the middle, and then they have oxygens on the ends, like a tetrahedral shape. But you notice they left the dots unfinished here. There's one electron missing off of each one of these. And that's so that you could see that when you put it in context of the structure of quartz, what you have is a bunch of these little tetrahedrons that are interconnecting between silicon atoms. And so the oxygen's connected on one side, right, to one silicon atom, and then this other dot will connect to the other one. So that's what they're implying. So silicon can make four bonds, and so it makes 4 bonds to 4 different oxygens. And then those bridge between the silicon atoms. Now, if you take silica and you get it above 1500 degrees, it'll melt and form a sort of red, hot, blobby mass. And if you cool it really fast, that's what we call glass. And so that's how glass gets made. But 1500 degrees is a very high temperature. And, you know, silicate glass or silica glass is really useful because you can make windows out of it, right? Glass. You can make drinking cups out of it. It's a very good insulator, electrical insulator. It's not listed here. But it's also a very high temperature. Silicates melt at a very high temperature. So what the Romans did is they developed something called soda glass. And what you do is you take sodium carbonate and you mix it with silica, and the impurity of the sodium in the sodium carbonate lowers the melting point of the silica a lot. And this is actually a property we'll talk about a little bit in the next chapter. It's called a freezing point depression. But the impurity causes the silicate to have the mixture has a much lower melting point than the pure silica. So then that allows us to do things like blow glass, like when you've seen these people take glass and they blow it up into a big giant ball, right, and they make a vase out of it. Or you see the guy at the Fresno Fair who makes the little unicorns and things with the hot glass. Really what they're doing is they're using soda glass, and a lot of it's been colored, but they'll use soda glass because it's much easier to work with. So vitreous silica is what you get when you take pure silica and you melt it. It's very hard. It again has similar properties to regular glass, but one of the things is it's transparent to ultraviolet light. Normal, like regular glass, because of the impurities and the sodium that's in it, isn't actually that transparent to ultraviolet light. It's really expensive to produce simply because it requires high temperatures. And then we talked about soda glass. Soda glass is what we use for most windows, and so this is that, including the sodium um, in the silicate, right, causes it to have a much lower melting point. So transparent to visible, but not ultraviolet light. Relatively high thermal expansion, but neither one of them is very electrically conductive, and so that makes relatively good insulators. Uh, Soda glass tends to crack. It's not as got as high a tensile strength, I think, as like silica glass or fused silica, and so it has a tendency to crack when you put it in water. Another type of glass is known as borosilicate glass, and this is what we call Pyrex. And what they do is add boric oxide to it instead of calcium oxide. So it has less thermal expansion, and it can withstand cooling cycles that would like normally shatter a piece of heated glass. So a lot of our lab glassware is made out of borosilicate. Pyrex, right? The Pyrex glass containers you have in your house are the ones you can use in your microwave and not worry about them breaking. And then another type of glass that is not as common as before, but it's mostly used sort of as a decorative glass, is called leaded glass, and they actually put lead oxide along with the silicon dioxide, and it has a much higher index of refraction, which basically means it reflects light better. It gives sort of that sparkle to the glass, and they also say it makes a ringing sound when tapped. I didn't know that one. But the problem with leaded glass is if you put things in it that are slightly acidic, it tends to leach out the lead and you end up drinking it. So there's some health concerns around old glass, like lead glass, that people have. It used to be really common, though, that you'd probably still find some around like your grandparents' house or in thrift stores and stuff. So you have to be a little bit careful about buying some of that stuff.